Hello, everybody. My name is Vasilis Ftenakis. I'm a professor at the Department of Earth and Environmental Engineering at Columbia University and the director of the Center for Life Cycle Analysis there. Today, I'm going to talk very briefly on electricity from sunlight. That is a topic very close to my heart. Energy is the biggest challenge that humanity faces in view of a growing population and with so many billions of people that want to improve their standards of living. There are several challenges, obviously, in this situation because the finite resources, they won't last forever. And we're talking about food and poverty and water and terrorism and education. I will put energy at the top of this because if we resolve energy, then we can even produce fresh water, we can produce food, and we can address poverty and so on and so on. In this slide, you see the expected growth in the demand of energy globally and for the next 20 years at this point. In the developed world, in Europe and the United States, we expect a growth per year of 1.5%. But in Asia, especially China and India, we expect a much higher growth rate. And Africa will start coming into play. It's not depicted here, but by mid-century or the turn of the century, we would expect that we would need a lot more energy in Africa as countries there would like possibly to take the same pathways towards improving the standards of living. Now, solar electricity. It is not a new technology. Actually, the photoelectric phenomenon, and photoelectric comes from two words, phos in Greek, that is light, and volt is from Alessandro Volta, an Italian physicists who contributed into this topic in the 18th century, about mid of 18th century. And the one who actually examined and understood and analyzed the phenomenon was Albert Einstein, and he got a Nobel Prize for that in 1921 for explaining the photoelectric phenomenon. So what is that phenomenon? There are certain materials, they're called semiconductors, that when they're exposed to light, they can free electrons from the valence into the conduction around the atom, and then those electrons, they can travel into the crystal and they can be collected by electrodes, by the wires that you can see in this schematic, and can lit electricity bulbs, and they can power supplies and so on. So the technology is not really very new, but what is new is that we put a lot of resources in developing these technologies over the last 20, 30 years. As a result of this, we have several technologies. We have the first generation, the ones that they were developed in the 70s, and we have the second generation that they were developed in the 80s and 90s, and a third generation that is evolving that is very, very promising. All of these have a very beautiful and bright future in front of them. Now, why so many technologies? Part of the answer is that the solar spectrum that you see on this slide, it is wide, all the way from the UV from about 0.1 micrometers wavelength all the way to the IR that is about 3 micrometers in wavelength. And the materials that I mentioned, the semiconductors, they cannot harvest all this. They can harvest effectively only part of that, a narrow part of that. So if we have semiconductors that they have a relatively wide wavelength, it can harvest more photons, but not the very energetic ones. If we have a semiconductor that can harvest the very energetic ones, some of these actually will be lost into heat, and some of the other photons will be thrown away. So it is a balance. We want semiconductors that they can give the best or the higher product of current times voltage, because that is power. So many photons, but also energetic photons. And in this schematic, you can see the energy band gap. That is the energy that a semiconductor needs to free the electrons for different semiconductors, for the common ones. Like silicon, it has an energy band gap of about 1.1, and you have the thin films that they have energy band gap of about 1.5. Now, the curve that you can see there, The dotted line, it gives the current record efficiencies for these semiconductors in converting photons into electrons. The red line, that's the Shockley-Queens limit. It is a theoretical limit for semiconductors efficiency when you have only one pair, only one junction, and the light is unconcentrated. If you put one at the top of the other, you can get to about 50%. But let's talk now about the simplest configuration, that is just one pair of semiconductors, and the interface between the two, it is the pump that throws the electrons away. So about 30%. Now, the commercial picture is a little different. We have small cells up to 25% efficient. When we go to the modules, those are the big panels, like 1 square meter that you can see on the roofs and so on. The efficiency is up to about 20.5% efficiency. Now, what you needed to remember about this, that there is this gap, the gap between the cell in the commercial production and the theoretical limit, and the gap between the big module and the small cell. Those are engineering problems, and we expect that this gap will be bridged in time. So we expect that the efficiency of the commercial modules will go up with the current technologies closer to 25%, 28%. And we have the newer technologies that they're evolving very rapidly, and we expect those to get up as well. Now, let's talk a little bit about the market. Why the market? It has been very, very, very important in also improving technology. When the market was created, and the biggest driver in creating the market that happened over the last 10, 15 years is Germany. Germany, that doesn't have a lot of sun, actually less than half of the sun that we have as, in our United States Southwest. Because of policy, they gave incentives to solar and wind. They wanted to go away from fossil and nuclear, so they created the market. And that market, actually, you can see the measure of the growth of this market in terms of year-per-year installations. We got from only a few megawatt back into the beginning of last decade, with the German renewable portfolio standard into about 300 actually totally, or 70 per year these days. Now, this shows the sum, the cumulative, and the last bar, about 300 gigawatt, is what operates today all over the world. Germany is still a big part of it, but you may notice that China actually has come into play very, very strong. And this is a picture that was created over the last 3-4 years, since 2012, 2013. And China is the biggest actually producer. You can see that together China and Taiwan is most of the production. China by itself about half of the global production, but China also, it uses about a third of that production. And this is again a development that happened over the last few years. China is ahead of everybody else in terms of not only producing, but in terms of using photovoltaics. And we expect that this will continue, but the United States is also coming strong. Now, with all this market, we're talking about economics of scale. Everything becomes cheaper, everything becomes better. The companies get materials for less, obviously, and everything, the equipment costs less and so on, and also they invest in R&D, so the technology is getting better. And you can see that, you can see the reduction of the price of the basic component of a photovoltaic system, that is the module, the plane. You can see it in this curve. This is what we call learning curve. And the slope shows what is the improvement in terms of price with every doubling of the cumulative capacity in photovoltaics. The price goes down by about 20%. So it is a progress ratio of about 0.8, 20% improvement. The new price is 80% of the previous price. And you can see the prices for the two major technologies. One is crystalline silicon, is about 85% of the market, and the other is cadmium telluride, that is a US-based technology. And it started later, but it's actually still the lowest production cost type of technology. People in Arizona and South California already pay less in their bills when they get solar electricity than electricity from the grid. Now, the green band there, it shows the price of photovoltaics, and it is arranged because it's cheaper in Arizona and California. Nevada is cheaper where you have a lot of sun than in New York and Canada, obviously. And the yellow band shows the prices of electricity in the different regions. The two overlapped already in 2014. So this is what we call grid parity. The cost from the sun of electricity is not higher in many parts of the country and in many parts, sunny regions of the world, than electricity from gas, coal, or other. Now, we expect that by 2030, this will be the situation all over the country. And where do they sell? Houses. This is the system of my house. I have it there for 20 years. Although the inverters came with a 5-year guarantee, I still have the original inverters. And it happened to think that those are beautiful. You can see the skylights on a place, on the research center in the Netherlands. You can see, the skylights up in an aquarium in the United Kingdom. Even when you put them on the ground, they don't have a high profile. Some people don't like wind turbines. I do, but they are gigantic. But these are small. They're small, relatively small. They're tilted, so they look great even outside, outdoors. And you can see here an aerial picture of a system that blends so well in the landscape in Germany. Really, I think that those are visually very, very, very pleasing. And also, they don't damage the land, they don't disrupt the land. You can have lawn between the two, between the arrays, we call those arrays, and they need to be spaced so that one won't shade the other. You have environmentally friendly installation there. Now, it's also versatile. You can put them not only at the top of a roof or facades, but in this case, just across a highway, and it has a dual use, not only electricity producer, but also a sound barrier. In China, that is the new production, as I said, and this is a system by Trina. That's the biggest in the world PV company at this point, based in China. And they develop a lot of projects in China. This is on the desert, close to the Gobi Desert there. This is an aerial picture of the same. It looks beautiful from the air. In the United States, up to about 5-6 years ago, this was one of the biggest systems. This is in Springfield, Arizona, in high altitude, and we have studied this very, very much for our life cycle analysis, about 5 megawatt. But this situation changed over the last 2-3 years. This is a 550 megawatt system in South California, developed by the biggest US company, that is First Solar, based on thin films. And it's as big as a coal power plant. 2 of those will make a nuclear power plant, so less than 1 giga, but more than a half a giga. And from the top, from there, again, it looks very beautiful. So where do we go from there? Actually, with my collaborators, Zweibel and Mason, we projected back in 2008 that solar electricity, together with electricity from wind and other renewable resources, can be the major contributor in electricity in the United States, up to 70%. And we have several studies that they documented this in terms not only of prices, but in terms of all the sustainability metrics. A lot of materials, minimum environmental impact. Obviously, this can be an answer to the climate change challenge. I hope that this will be inspiring enough for all of you to look more into this type of technologies. Solar and wind, renewable energy, that can be the answer to our energy and climate change challenges. Thank you.